Hey there, so welcome to our third video in AP Chemistry. So we're still dealing with the introduction, topic A, and video 3, states of matter. Like I had mentioned before, make sure that you're referring to our textbook, in this case pages 5 and 6, for further information. So we're going to talk about matter, the 3 states of matter, and then changes in states of matter. So matter is anything that has volume and mass. So kind of like I said before with make sure that you write stuff down, well, volume is anything that occupies space, and mass is pretty much the amount of an object, or amount of atoms in an object. So again, make sure that you write down those definitions for volume, anything that takes up space, and mass, the amount of matter, amount of atoms inside of an object. Alright, so let's talk about the 3 states of matter. We've got solids, liquids, and gases. Solids have a definite shape and a definite volume. So we can take a look at a cube or a clump of clay, whatever it is. It has a shape and it has that specific volume. So even if you manipulate the shape, the volume itself would still occupy the same amount of volume. These particles are packed very closely together and they will vibrate. So what I want you to take a look at here, and we use these a lot, these are called particle diagrams. So these represent, each of these little red spheres represent something like an element or a compound. So say for example, each of those red spheres, whoopsies, let's make those red instead. So any of those red spheres would represent, in this case, we might say it's iron. So a lot of times we'll have a key, so that red dot is equal to iron atoms. Oh, by the way, my stylus is really awful, so I apologize. I'm trying to get a better one, but I doubt I'll get one anytime soon. Anyway, so each of those red dots represents atoms of iron. We show these particle diagrams for us to kind of visualize what's happening with the particles themselves. If you notice that they have these little like parentheses around them, that's showing that they're vibrating. So no matter what solid object you have, like say for example a piece of wood, even though it looks like it's standing still, no matter what, those particles are still slightly moving. They're just vibrating, but still hanging on to where they are. So we have crystalline solids and amorphous solids. So crystalline solids are kind of like table salt, NaCl. They are really packed together. They don't move around very much, versus something amorphous would be like glass. So glass, I don't know if you've ever seen this before or heard about it, but glass is essentially kind of like a fluid. It's constantly moving. If you take a look at really, really old homes, and it's kind of hard to have them here in the U.S., but even in Europe, and you take a look at their windows, you'll find that the top of a window pane is much thinner than the bottom because essentially those glass particles are moving down. It takes a lot of time for it to happen, but that's kind of why we call glass amorphous, an amorphous solid, even though it kind of looks like it would be a liquid in terms of what the atoms are doing, but it just takes forever. Anyway, so with these solids, again, you're going to draw these particle diagrams really, really close together, these little spheres close together. If we take a look right over here, so we have pretty much cubes of, I don't even know what they are, so we're just representing them as being really, really close together and a very nice uniform structure. Next we have liquids. They don't have any definite shape, meaning that they take the shape of any object that they're in, but they do have a definite volume. So even if you took some liquid, put it into a graduated cylinder, and it's 75 milliliters, if you take that same amount of liquid and pour it into a measuring cup, still going to be the same amount, same thing with the beaker. The volume is always going to be the same. In liquids, the particles are a little bit more freer to move. If you notice here, in the liquid particle diagram, they're spaced apart just slightly, just a little bit more. And if you've never taken physics before, you probably haven't seen these. If you have taken physics, you know what they are. They're vectors. But essentially, they're showing you where those particles are moving. And all these little vectors or arrows are really short, meaning that they do move around a little bit, but not as much as gases, like we'll see in a second. So if we take a look over here, you see that we have liquids. Again, they're not that tight, compact structure like we've seen with the solids. They move around a little bit more. Gases don't have any definite shape or definite volume. So with that volume part, it means that they are compressible. Alright, so solids, we can't push them in any further, but gases we can. I don't know if you've seen this before. It's essentially a piston. But we have this space right here, and this object kind of pushing in all the particles that are inside. So those gases are compressible, meaning that their volume can change. So again, all that space in there, that's the volume. So gases do not have a definite volume. They can move freely. In fact, they move all over the place. I'll show you some simulations on Colorado FET. If you've ever taken physics, essentially, you may have used those FET simulations before. But if you haven't, that's fine. I'll show them to you as well. So you can see that these vectors are essentially moving really, or they are very large. These particles are moving all over the place. If you also notice, this container doesn't have a lid to it, so these particles can leave the container as well. So many times we show like a box or a closed container to show what those gases would do inside. Kind of like over here. So we see that there are fewer particles and they're spread out really, really far apart. This is something I do want to make sure that you draw this as well. So this is essentially phase changes. And you've seen this before, but I want you to have temperature on the y-axis and time on the x-axis. And essentially we have these lines. So we have a slanted line, then a horizontal line, followed by another slanted, horizontal, slanted. So you're going to have 3 slanted, 2 horizontal lines. Each of those slanted lines represents the state of matter. So the first one, since the temperature is low, it's going to be a solid. Then as we increase the temperature, it becomes a liquid, and then a gas. So these are all your particles and what they look like inside of each of these states of matter. If you notice, the solid particles are really close together, whereas the gases are very far apart. So the horizontal lines represent an equilibrium. So you'll see that we have solid and liquid, and that double-sided arrow. The double-sided arrow represents that there's an equal amount of solids and liquids. I might also draw them like this too, so make sure you show both of them. Then we'll talk about each of those phases. So solid to liquid, melting, liquid to gas. We have 3 different terms: evaporation, boiling, and vaporization. Going backwards, liquid to solid is freezing, and then your gas to liquid is condensation. Now we can also go from a solid to a gas, and if you remember that from earth science, that's sublimation. And remember, my stylus is awful, so I apologize. That's sublimation. And then a gas to a solid, that is something called deposition. So these are all phase changes, and these also happen to be physical changes as well. We'll talk soon about chemical versus physical changes. So pretty much to summarize, we've got solids, liquids, and gases. Make sure that you know their properties, so if they have a definite shape or a definite volume. Also know how to do the particle diagrams for those and the phase changes for each. So let me know if you guys have any questions. Take care.